Knowing that the computer represents the world with zeros and ones, how does the computer represent complex objects like addresses or users? Concepts like these are beyond just numbers and characters. Today, we are going to talk about object-oriented programming. Object-oriented programming has become a super important paradigm in programming. The idea behind it is that you can represent concepts from the real world that can have complex relationships between them. Objects have internal fields representing the data or state, and also functions that allow to modify such fields. Object-oriented programming allows us to create different instances of the same object, with each one having its own identity. For example, we can represent in an abstract way a user where each one has his or her own email, name, etc. We can also use objects for building complex structures where, for example, we can have an address object that has a list of members that live inside of that household, where each member is a person object with their own fields, as explained before. Effectively, this way we can create, for example, a town with addresses and store which people live there. Each one of these copies is called an instance. Objects are derived from templates or molds. Those templates are called classes. Classes can have their own members or attributes that, once modified, affect all the existing and future object instances. We will review static versus instance variables and methods. Now let's look at what a class looks like, okay? This is the basic structure of a class, and maybe it looks a little bit overwhelming at the very beginning, but we're gonna be looking at it section by section. So the first part is where the name is. We see the keyword public. That means that everybody can access it. We're gonna talk more about it during the encapsulation part. We see the keyword class, which essentially is defining that it's telling the compiler that we're gonna be defining a class. And then the last thing is the name of the class. So in this case, the class is named myObject. Then the next set of elements is the members. And the members or instance variables are just values that determine the state of the object itself. If we were defining like a vehicle class, like, if you were writing the database for the DMV or something like that, you could have for a car, certain fields that represent the make and model and license plate of your car and who's the owner. So those per instance members will be available. So they also have their access control keywords, but let's ignore those again until we touch the encapsulation part of things. If you can see, they are defined like normal variables, where you see that there's an int member1, boolean member2, and it's initializing to a different value than 0, or in the case of a boolean is false, the default value. And the last one is using an example of a static, but we're going to talk more about that later. Then the next thing is a constructor. The constructor is essentially a method that has only a return type and no name, if you want to see it that way. And the return type is the object name. For example, in this case is myObject, which matches the class. And in this case, it has no arguments. So it's essentially going to initialize, for example, in this case, member to just a random value. This is going to be called whenever we use the new myObject parentheses. Every time that we do that, it's going to call this constructor. And then the last block is just methods. So we're going to talk more about in detail of all these concepts, but it's essentially the basic ingredients of an object. So we've talked about instances in the past. How do we create instances? Well, it is by calling a constructor method using the keyword new next to it. The constructor allows us to initialize an object, and a constructor also looks and works like this. So in a constructor, the elements that we see, if we just isolate the constructor, we're gonna see that it has a structure like this, where basically we have the access modifier, where you can see that it's public, and that means that the class, the package, the subclasses, and the entire world can access it. Protected means that the class, the package, and the subclasses will be able to access it. And private, that means that only the object, the things that are defined on that class are going to be the ones that are going to be able to modify it. The next thing is the name, which I just want to emphasize that whenever we call that method, we're going to assign the pointer called this to the instance of that object. The next item is just the arguments and the variable sent to the constructor. Once initialized, the class creates a copy of the object with a pointer to itself. And just like all of us know that me, whenever we call me or say me, it's our own instance, our own person. The object has a very similar reference and it's called this. Also, it knows who the parent class is and is referenced as super. We will talk more about this in a little while. The internal values or instance members or attributes can be modified either directly depending on the access modifiers of those variables. For example, public, private. We'll talk about those in a little bit more with a bigger detail. But we can modify them if we need to. Indirectly, we can also modify those values by going through methods or functions. Generally, functions are just a set of operators that have inputs and produce an output. Now, let's look at how a function is structured. A method is very similar to a constructor where you have the access modifiers. In this case, we do have a return type, which is directly typed to the last line of the return method, because it's essentially, unless we have a data type void as a return type, every other time you will need a return statement, meaning the keyword return and then the data that it's supposed to be returning that matches the return type. The next thing is a name, how we're gonna identify that method, and then the last part is the arguments that are going to be sent to the function. Between both curly brackets, the opening and closing one in the method, that's the function itself, that we're going to inject the code that it's going to be working in there, and that's how we're going to pass, quote, quote, the recipe for the code to be working. Now let's talk about the basics of object-oriented programming. Object-oriented programming was born in the late 70s, early 80s, when Xerox, the company for the photocopies, was starting to play with their research labs. And oddly enough, Xerox developed this language called Smalltalk, and it contained the basics of the object-oriented programming. The rest in the push of object-oriented programming history is kind of computer history, because one of the early guests to this Xerox research lab was nonetheless Steve Jobs, who was impressed by concepts like object-oriented programming, and also this guy, who then Apple introduced to the mass market. Xerox kind of failed to put all that good research into the market, so Jobs took the opportunity and ran with it. Other languages like C++ then later try to grab the language of C and add object-oriented programming to kind of evolve it and introduce an object-oriented programming language concepts there. But when Java was designed, C++ was too complex because you had to manage your own memory, you had to do certain other very complex tasks, and it was mostly what I was telling you about in the last video, where it's difficult to port data seamlessly. So Java kind of became the flagship of object-oriented programming. But enough about history. Let's keep talking about object-oriented programming from the main characteristics that it has: encapsulation, inheritance, and polymorphism. Let's talk about them in greater detail. Encapsulation. Encapsulation allows us to restrict or hide access to the object's components. A great reason to remember this is validators. For example, they help us protect the data, because in some cases it's actually really important to remember that if you put garbage into a system, you're going to get garbage out. So for example, let's look at the following class. In encapsulation, like I was saying, it's really important to keep good data in a system. So encapsulation allows us to control how we're going to accept certain data if it actually works fine. So for example, let's assume that we're going to set an email, and we're going to, because emails is just a string of characters that has a very specific format, we define that the email in the class is going to be a string, and it's going to be called email. We can see here that we are defining it as a private string, and because it has a keyword private, that means that we cannot directly, a user cannot do user.email and start modifying it. So we have to use getters and setters to try to modify the entire the variable. So in this case, for example, we're saying that the keyword set email receives a string and throws an exception if it doesn't match the validation that we're looking for. So for example, we can see that the email is trying to figure out if it contains an @ sign and a dot. If it doesn't have those two things, most likely we're not receiving an email address. So if I type the keywords ASDF, it's essentially not going to validate it. So unless I have what looks like an email address, I can then accept it and store it as an instance variable. And then the other one is, how are we gonna read the email? Well, we can then say that we can write a getter function, and that getter function is gonna give us the email address. Now let's move into polymorphism. Polymorphism means many forms. The simplest way to think about it is by having functions that take different types of parameters with the same name. For example, a function add can be written with 2 floats or 2 ints using the same name. Let's look at the code. So in this case, we can see that there are 3 add methods. And if we were going to put this on code, and let's just probably open up our IntelliJ. Let's assume that we have this code where we were going to write public static void main, an entry function, a main function, string args, and then we did calculator c equals new calculator. So if we were going to do c.add 3.0 f and 2.0 f, it would essentially call this guy. Right now it just has that remove that gray because it's adding coverage. So if we did c, then if we did 3,2, it's gonna essentially detect that we've added coverage of this, and c.add 2,3,2, it is essentially resolving to this one. And so you can see clearly how IntelliJ, you can see clearly how Java has essentially the same function being called, but just depending on the arguments, it's gonna try to resolve it. And what that is known as is that Java needs to have for every function a different signature, so that way you can accept it as polymorphism. Why? Because the signature is essentially the name of the function and the arguments, not the return type. Because otherwise it would just create for confusion. So for example, if we say that this one with the 2 parameters, even though I'm accepting 2 floats, if I added another function exactly the same, and I called int, and if it would be returning an int, that's why the return type is not part of the signature, because you can see how now it's like saying, hey, there's 2 functions and both of them match, because in this case it really doesn't care about the return type. It's just about this part of the function. This is the signature. So as long as they have a different signature, it's gonna very easily distinguish which function to call. Polymorphism can also refer to the subtyping, where the methods of subtypes have the same names but perform different things given its nature. A drive method is not the same for a motorcycle, for example, than it is for a plane. A plane and a motorcycle, they move and transport quite differently, but both are vehicles. The last component in object-oriented programming is inheritance. And that means that you have the capacity of abstracting concepts based on hierarchy. Just like we were talking about vehicle, motorcycle, and airplane. Technically, all of those are vehicles. Inheritance allows us to just abstract that hierarchy, very similar to this Wikipedia entry for primates. So if we go into the primate, you can see here that there's a very nice tree of hierarchy, and we can see very clearly how essentially humans are. We can see very clearly here how humans are related to gorillas or chimpanzees, and it's all about the inheritance. So the class Homini would have two subclasses called humans and chimpanzees, and so on until we have, you can see all this genetic tree that we have until Boreoeutheria. Inheritance allows the child component to have the same methods as the parent, but it also can override them to make them particular to that child component. For example, so then here we clearly have the idea that we have this. So we have a very clear idea here that we have desserts, and that we're gonna have three subcategories: cake, ice cream, and cookies. And then we're gonna have different instances of each one of those. So we can see that, for example, there's a chocolate cake, a cheesecake, a wedding cake. In ice cream, we have vanilla cake. We have vanilla. We have sorbets. We had frozen yogurt. And in the cookies, we have different types of cookies: chocolate chip, double chocolate chip, macaron, Oreos, whatever. So inheritance, we can see, for example, we can see how we're representing that on the code. And the best way to represent that on the code is by using the keyword extends. And we can see we do have keyword extends. Whoop. We do have this guy here, which is a keyword extends. It's essentially copying all of these guys here into being into this class. So because we've copied all those things, if we call attributes car, you can call the attributes function, which is copied, and it will print all these color, speed, whatever way that we initialize it, plus all the new extra features that we've added. And just like we said before, the class creates a pointer to the intermediate available ancestor with the name super. And we can see here very clearly. As far as super goes, you can see that each instance has a pointer to itself by using the keyword this, and then we also have a pointer to the parent class, which is this cookie guy here, and it's referenced by the keyword super, and the cookies class has a pointer to the parent class, which is referenced also by the keyword super. Isn't this super? Now let's look at some code to explain the usefulness of the super keyword. A good example here is that we have our cookie class, which has a series of ingredients, just these guys here. And as we receive the new ingredients, we add the ingredients and then we mix them. And then the function here that represents the mix is essentially just saying that it's gonna shake all the ingredients and put them in a random order, essentially simulating what we would do with a mixer, and that essentially mixes all the ingredients together by doing it 5 times, where it's swapping all the elements. In this particular example, we do have that the chocolate chip cookie is essentially a cookie with extra ingredients added once it has been mixed. So if we had the eggs, the milk, the sugar, the flour, after we mix all that, then we can add the chocolate chips on top. And because of that, the mix method, we're overriding the mix method. Right here, we're overriding the mix method, but also we are doing the traditional mix and then adding the rest of the ingredients on top. So we're doing the mix of the butter, milk, sugar, whatever, and then afterwards we're mixing more ingredients, which are the chocolate chips afterwards. So this is a good way to represent when we actually need to call the super method, because we want to preserve the initial behavior and extend it. To verify if an object belongs to a particular family, we can use the keyword instance of. For example, it's a good way to remember about checking if something is. For example, if we want to verify that only the class student, or in this case, we want to check if Cookie Monster is going to be able to eat these cookies, we can actually check if any of the fancy cookies that we have is an instance of Cookie. So any class that inherits of Cookie is going to return true for that statement query. So therefore, Cookie Monster is going to be able to eat it. If we had another type of instance being passed, then Cookie Monster would not be too happy. Now this part is very important to remember. Let's talk about how complete an object can be. So one thing that is quite important here is in this chart that we are already familiar with, about the dessert, the ice creams, the cookies, is to highlight that we have one very interesting concept in here. Close. We do have a very interesting concept here, where the higher we go, like for example, dessert, is a very abstract concept. It's a very incomplete idea. You just know that a dessert, when somebody tells you, do you want a dessert? Usually you don't choose a dessert, you choose a concrete item. When they bring you the dessert menu, you don't say, oh, just bring me anything. You just choose whatever you're feeling in the mood like. Like for example, you can say, oh, bring me the chocolate cake or the ice cream that I want to get. You never just say, oh, just bring me the dessert. So the idea is that the higher we go on these type of three elements, we do have a situation where the idea is that you're more in the realm of ideas. You're more in the realm of ideas, and the lower level that you go, you're more in the concrete side of ideas. So Java does provide ways of keeping certain things more like, how do we define that a dessert is a dessert, even though that we technically don't have an idea of what are the desserts that are going to be served. We just know that certain requirements need to happen, for example, it being sweet or being served at the end of the dinner, that those things are the requirements for a dessert. Whatever implementation it is, well, we don't know, we don't care, because right now at the moment when we say we're going to serve dessert, we don't have an implementation. There are certain other concepts like cookies, ice cream, and cake where we can have something more, a little bit more defined, where we can have some implementation ready, but not all of it, because so we don't know exactly, if these three cookies right here have very different methods of being created, same as these guys. All we know is that a cake is baked, that it has certain basic ingredients, and they have certain decorations. So from that perspective, we can assume that the cookies, ice cream, and cake could be abstract classes and have some implementation, but we are not going to force the user to start using those right now. The last idea is just the traditional classes where we have full implementation or full code available, and when we are writing the actual directly to the user type of code. These two guys are much more useful when we are building APIs or we're defining the rules for a software. So for example, a plugin system, we can just say what is going to be the shape of the plugin or the puzzle piece, without really having to define exactly what is in that drawing of that piece. So let's look at those three ways that we define the interface, abstract, and classes. So an abstract class, it just has the keyword abstract at the very beginning, and you can see also that here we do have a method that it has no code. It actually even has a semicolon at the very end, but it does have an abstract keyword. What that means is that this class will not be able to be instantiated. In the same way that if you just say, oh, I want a cookie, well, without it being more concrete, you cannot just have a cookie. You can have a chocolate chip cookie in the real world. You can have a snickerdoodle, but you cannot just have a cookie. Now, you can choose just give me anyone, and that's probably fine, but you cannot just create a cookie without knowing what the cookie is going to have. So, in this case, I decided that I would define the abstract method as decorate, because cookies can have very different decorations. And that means that any class that subclasses this guy needs to implement this function, needs to have code for this function. And it's a mandatory thing. Otherwise, he will say either define it as abstract, or, which means adding this keyword, or define it as a traditional class. An interface is the opposite extreme. So we went from a class that has all the code that we need to an abstract class that might have some, you can see that the word mix, all these dots represent that there's actually code written down. I just wanted to keep it very simple so that way visually you guys can actually understand that. But the interface has no code. It just is essentially a collection of abstract methods. Before we move on to the exercises and code samples, I'd recommend you to subscribe to the channel to get notified about new videos as they come out. Thank you, and see you around.